Hello everyone. Our project is titled YOLO-Driven Fine-Grained Detection in Remote Sensing Images. Our team members are Eshika, Mazik, Sowmya, Srigana, and myself, Tejesh. I'll begin with the background and motivation. So, remote sensing images come with several challenges. Objects appear extremely small, they're randomly rotated, heavily overlapping, and they often blend into the background. Traditional detectors usually miss such objects or produce unstable bounding boxes. So, our motivation was to build a detection system that can identify small, fine grained, and rotated objects consistently while remaining efficient enough for real time applications like surveillance, traffic monitoring, and disaster assessment. So, going to the next slide, literature review. So, from the literature, we see that different object detectors have different strengths. Two-stage models like faster RCNN and mask RCNN detect small objects well but are slow. YOLO V4 and YOLO V5 are fast, but their horizontal bounding boxes cause issues with rotated objects. Rotation-aware detectors such as REDET and S2ANET solve the angle problems but are heavy and computationally expensive. So overall, the field shows a clear trade-off between speed, rotation robustness, and fine-grained accuracy. This gap is what we address in our system. So next slide. This is the comparison table of existing methods. So this table highlights how existing models perform across different categories. Some prioritize speed, some focus on accuracy, and some handle rotation well, but none offer a balanced solution for aerial imagery. This guided our design choices. So, going to the next slide. So, gaps in literature. So, we identify some key research gaps from the literature. Detecting tiny objects is still difficult. Angle prediction is unstable because of angle wrapping. Rotation aware models are often too heavy, and most existing systems don't include practical components like vehicle counting. These gaps shaped the improvements we introduced. So, next slide. So, this is the system architecture. We structured the pipeline into three categories. First is preprocessing, where we resize images, convert polygon annotations into rotated bounding boxes, and normalize angle values. Second is the YOLO detection module, which includes our enhancements such as circular smooth labeling for stable orientation learning and CBAM attention for focusing on important regions. And the final stage is the integration layer, which runs inference, visualizes detections, and handles features like vehicle counting through a Flask interface. Overall, it's a modular and efficient end-to-end system. So, moving to the next slide. This is the module connectivity diagram. So, it shows how the modules are connected to each other. The pipeline is fully modular, meaning we can switch from YOLO V5 to YOLO V8 without changing the rest of the system. This makes the approach flexible and easy to update. So, this system consists of three modules: data preprocessing module, module, and integration module. So, next slide. Dataset preparation and spreading. So, we use the DOTA and FAIR1M datasets, which include the thousands of dense and rotated objects. We converted polygon annotations into rotated bounding boxes, normalized angles, applied multi-scale resizing, and cleaned the dataset. We also used augmentations like mosaic, random rotation, and brightness changes to improve generalization. So the pre-processing steps we did were image resizing and padding, annotation conversion, angle normalization, data cleaning and balancing, caching and batching. So next slide. So orientation handling with circular smooth label. So orientation is a major challenge because angles like 1 degree and 359 degrees are visually similar but numerically far apart. Circular smooth labeling transforms the angle into a smooth circular distribution. This removes angle discontinuity and helps the model learn rotations much more effectively. So, next slide. So, this is a YOLO architecture enhancements and training strategy. So, we enhanced YOLO v5 and YOLO v8 with CSL and CBAM. We used AdamW optimizer, mosaic augmentation, and adaptive LR scheduling. YOLO v5 provided fast interference while YOLO v8 offered higher accuracy thanks to its angle-free detection head and deeper architecture. Testing both of them helped us understand the balance between speed and performance. So, next slide. Real-time vehicle counting via Flask interface. So, after the YOLO model performs detection, we filter only the vehicle-related classes such as cars, trucks, and buses. We then compute the final count automatically. The Flask interface displays the annotated image with rotated bounding boxes on one side and the total vehicle count on the other side. This entire process runs in real time, making the system useful for traffic monitoring and urban analytics. So, next slide. So, these are the ULA V5 results. The model performed well on medium-sized objects such as cars and buses, but struggle with very small or densely packed ones, which is expected based on prior studies. So, based on the performance, the precision improved from 66% to 73%, and recall from 49% to 71%. These results indicate reliable detection aided by CSL for better orientation accuracy. So, coming to YOLO V8 results. So we achieved around 79% precision, 76% recall, and close to 80% map at rate point 0.5. Your V8 handled small, rotated, and overlapping objects much more effectively due to its stronger backbone and anchor-free design. So this model performs well on small, rotated, and dense object regions. This is the vehicle count integration output. So this slide shows the final result generated by our Flask interface after the detection step. Once the YOLO model processes the uploaded aerial image, we filter only the vehicle related classes such as cars, trucks, and buses and calculate the total count. The interface then displays two outputs. On the left, the image with the rotated bounding boxes drawn, and on the right, the automatically computed number of detected vehicles. The entire workflow runs in real time, usually just taking a second or two from upload to output. This makes the system practical for real world tasks like traffic density monitoring and large scale aerial analytics. Coming to conclusion, to summarize, our enhanced YOLO pipeline improves rotation handling, small object detection, and overall accuracy using CSL and CBAM. And the real time vehicle counting module demonstrates practical applicability. Overall, the system provides a strong balance of accuracy and efficiency for remote sensing tasks. And these are the references we used. And that concludes the system overview and results. I will now hand over to my teammate Srigana, who will walk you through the live demo of our system. Thank you.
So this is the backend system that provides our demo. The Flask app handles everything from file upload to running YOLO v5 and YOLO v8. Here the route accepts the image from the user and then the file is saved into the temporary folder so both models can access it. Before running the detection, basically the system clears all the outputs of all the previous outputs so that this prevents mixing results from earlier runs. Here the YOLO v5 is executed using the detect.py script through a subprocess call which it loads our trained best.pt weights. And then the YOLO V5 also writes the vehicle count into a text file. Here the for the YOLO V8 we are using Ultralytics API. Here the model is preloaded once the server starts, so predictions are automatically saved and moved to the static directory of the UI. So both the YOLO models run in parallel threads. This reduces total inference time. It also allows direct comparison between YOLO V5 and YOLO V8 output on the image. And after inference, the backend reads the vehicle count and prepares the final results page. So overall, this backend completes the full pipeline: image upload, detection, counting, and UI display. Now I'll show you the demo of running this live, where I'll run the app.py, and here it is running in local server. So I'm running the file app.py. It will run in the local server. As you can see, this is the main interface. Here we can select an image. So I've already created a folder in my local desktop. So yeah, I can use this. So the user can upload the image and there's no requirement of pre-processing here. So once I click on the submit, the server immediately sends the image to both YOLO V5 and YOLO V8. They run parallel threads. Here you can see, and the detection finishes faster as we can compare both the outputs side by side. Here the YOLO V5 output, here it uses our enhanced architecture with the CSL and attention models. It returns oriented bounding boxes and also write the vehicle counter text file, such as 42 here. And this is the YOLO V8 output. It generally detected more small and rotated objects. And the bounding box tend to be tighter compared to the YOLO V5. You can see the accuracy difference visibly in dense and or shadow regions. So everything you see here, uploading, predicting, counting, and displaying, happens in real time. The system is lightweight enough to be used for traffic monitoring, parking analysis, and general aerial image analytics. So I can also use this for identifying some different aerial images, such as this one. Here you can see it is also detecting ship. That's it with the demo. Thank you for being with us.